and I'm working on stimulated rewind scattering, which is a specific nonlinear optical interaction. Basically, what we're doing is interfering two light beams and using that interference to create the sound wave. And this sound wave then scatters light, which is something we can use, for example, as an amplification. And this is interesting from a communication point of view, because we can use this to process signals. We can see, for example, here I've built a microwave photonic link. Can you show that, okay? And by playing with the way I modulate my light and then amplifying the a part of it, I can create a notch filter like this, or by changing the modulation, I can switch from a filter where I remove one signal to a filter where I increase a signal. So this is something you can either use to remove a jammer, for example, or you can use it to amplify a signal that is of interest to us. Yeah, currently we're using a setup here that's completely fiber-based, which involves all of the components you see right now. But we are working on moving this to integrated circuits. So these are some examples of the samples we have, which we're testing. And besides using it for communication, stimulated rewind scattering is also a very interesting process. For example, in building lasers. So here I'm working with one of my students who is trying to use this chip and use on-chip SBS to create a laser with a very narrow line width, which can then, for example, be used for communication purposes, but also for creating atomic clocks, which require a very precise laser source. Beyond this, we can also use stimulated rewind scattering as a sensor. So we've got a student who's trying to build a temperature sensor that's based on stimulated rewind scattering, as it's a process that's based on sound, and the way a material moves changes with the temperature. Similarly, people are using it to build stress measurement devices. And also you can use it as a spectrometry device. So it's used in biological applications to look at samples and see what's contained there in chemicals. Yeah, so in this case, we're also using a lot of RF. So you're, as far as I understand, you guys have electrical engineering backgrounds. So we are using RF-like techniques. So we're using this vector network analyzer, which allows us to measure the transmission of an RF signal, which we then modulate onto the light and finally retrieve again after passing through everything here using a photodiode. I think this is a good example of things we can use in optics to enhance our experience in the electronic domain. And as you'll see in further presentations, there's a lot more we can do. But if we combine all of this, we can create an environment that allows us to increase the data transfer in our international communications, for example. Like we're talking right now using these kinds of optics, which allows us to stream all kinds of video across the world.
I'm working mainly in the microwave photonic field. So this is the area where we try to combine the photonics and the electronics part to actually process the RF signals in the optical domains. The easier way to, the easiest examples that we can see these days is in the server's direction. So you know that these days we transfer all of data using the optical fibers from the transmitter to the receiver. Those kind of photonic link is what we can acknowledge also as a microphotonics. So in here, I will show you one blocks in microphotonics that we call it as a programmable photonic integrated circuits or programmable PICs. the programmable peaks is here as a core of the microphotonics. Maybe you can imagine this as a microcontroller or FPGAs in electronics domain. So using this chip, we can create multiple functionalities such as filters, time delays, beamformings, and much more applications. It depends on our needs. And what is actually inside of this chip, you can see from this layout schematic. As you can see, this is the typical layout for the optical photonic integrated circuits. So it's kind of similar with what you see in the integrated circuits layout design. So inside of this chip, we have multiple optical circuits like ring resonators that has 4 ports, 2 inputs, 2 outputs. We have another ring resonators that can be double injected, that what we typically call as a flame, which is short for finer linear amplitude modulation elements, where it can shows very fancy responses that we can really utilize it for the RF applications. And yeah, it's have a couple another optical circuits. But then why it's interesting, because if you can see that there is a few route in yellow here, which is actually an electrical routing or electrical pairs. This is where we attach an electrical signals to program the response of the optical circuits into multiple responses. Now let me show you how it works. So first, I will send a broadband signals through an optical amplifier here. The idea is to improve the power level and at the same time also improving the noise that we put as a standard, like what you see in these signals. So let's say if I turn it on like this, then you see the response is changing. It depends on which optical frequency that we use now. And now let me activate the couplers like this. And we can see that the response of the signals are moving. And this is actually how we program the ICs or photonic IC regarding to our needs or regarding to what kind of application that we want to achieve. For example, this is when we adjust the rings as a notch response or bandstop response. Maybe some of you already heard that we have a filters in the RF domains. RF filters for to stop any RF frequencies. This is the typical notch filters that we can create, but also with the same chip, we can create a pass band. So, and a triangular waveguide, triangular response, sorry. So from these 3 examples is already shown the richness or the possibilities that we can actually achieve by having a programmable peaks in our chip. And later on in the next setup, we will show you how we actually use this kind of programmable peaks for integrated microphotonics.
In this setup, we work on curved frequency comb generation. This is a method of generating different frequencies, but are rather coherent. For microphotonic applications, that can be useful because on each data, for instance, to transfer, it would be more useful than have a whole array of all types of different lasers, all at their own length, because you can control it centrally. and the margins need to be smaller. Now, what happens here? So at the setup, this is kind of the heart of the setup. Here we have a small chip. This is also made of silicon nitride. This is produced in a different foundry at Ligentech in Switzerland, because they excel at having different type of waveguides where the light is more and in a smaller area for nonlinear interactions. At the moment, I am using a red laser for alignment, but most of the interaction happens in infrared. And right at the moment, yeah. So I have a microscope set up that you can see a top view of the chip. So at the left, you see a lensed fiber, which couples the light into the chip. And then on the right, it gets guided through a waveguide. In this case, here, coupled. And what this ring resonator does is it stores a lot of light. And it has very low loss, so it stores a lot of energy from of light. So if you pump it quite hard, you get so much energy in such a small area that it actually becomes unstable because there are some nonlinear terms interacting, and the light starts to modulate itself. So at right, we come in with a continuous wave laser. So this is a single wavelength. Then it gets to go through an amplifier such that we have enough power, and we connect it to the chip. So yes, we couple the light in, we put it through the resonator, and part of it gets coupled out, and then we check it with an optical spectrum analyzer. So here we have a spectrum that goes from 1560 nanometers to 1660 nanometers, and it spans quite a few. This is not a very pretty tone. This is one I generated this morning, because right now it's off because there is quite a lot of power necessary, and then everyone here has to work with goggles. Now, for the resonator, so here we have some different spectra. These were captured by a student that worked here, a bachelor student that worked here with me. He graduated earlier this week. So here we have a few resonances, and at these resonances, the light actually can be created, and this has a bit of a better resolution. So then you can see below in green, then is a kerchrome generated, and it has very specific frequencies. And in this case, it has a frequency of 25 gigahertz, because the spacing between the resonances is 25 gigahertz in the optical domain.
Well, the idea is that we want to convert the RF signal into the optical domain and use some optical components and device to process the signal and then convert the signal back, retrieve the RF signal we want. The reason why we want to do it is that in optical domain, we have large bandwidth and more flexibility in reconfiguration the response. Here, let me first show you the basic schematic of my setup. So here we first have a laser, a continuous wave laser, and then we have a modulator. We use this modulator to convert the RF signal into the optical domain. And then we use an optical filter for the single sideband modulation. And then we amplify this optical signal and send it into a programmable silicon nitride photonic chip. And this is the processor that we use to process the signal. And finally, we use the photodetector to retrieve this signal back into RF domain. And here at the upper, you can see this is a real photo of the chip I'm using. On the chip, it consists of 6 ring resonator, as I just illustrate here. Then maybe let's go to our real setup, and I can show each device to you. So here, it is the laser I mentioned. It is working in the wavelength of 1550. And then the optical signal is transmitted through this optical fiber. It goes to this phase modulator. We modulated the RF signal into the optical domain through this modulator. And then the modulated signal goes into this optical filter. We use this filter to create a single sideband modulation. And then the signal is sent into this optical amplifier. We increase the power level of the signal. After that, the signal goes into this polarization controller to control the polarization so that most of the light can transmit in the photonic chip with very low loss. This box, our photonic chip, it is actually in this box. And here we not only have the photonic chip, but we also have some heaters and the temperature controller to stabilize the response of the photonic chip. After this photonic chip, the signal goes to this photodetector, and then we can retrieve the RF signal back. And here is the wave analyzer that we use to generate a sweeping wideband RF signal that we can get the response we want. So here, let me show the response in our wave analyzer. So here, it is actually a response of single ring resonator. As we can see, it's actually, we can use this ring resonator as a notch filter in RF domain. As Aoki have already demonstrated before, he has a programmable chip that can generate different response. He already showed that in optical domain. And here I can show it in the RF domain, which I have more information about the phase. So here, the upper screen, it shows the amplitude response of our ring resonator. And the lower one, it is the phase response. And we can say if we change the coupling of our ring resonator, we can change the amplitude response and also the phase response. You see, now the notch becomes shallower and shallower. This shows the potential of reconfigurable or the programmable of our photonic chip. Also, we can set this chip in another state, what we call overcoupling state. You see, the phase response is very different from the previous one. As I said before, on this chip, we have 6 ring resonators. Here, I only activate 1 ring, and then it is also possible to activate more rings. We can have a look. Now you see, we now have, well, 3 rings in our, well, in this frequency range, and we can use each ring as a processor to process the amplitude, not only the amplitude, but also the phase of our signal. So we can have, well, tailor the phase and amplitude of the signal, then we can have some improvement to our system. As Aoki said before, we have done some work about using this ring resonator as a processor to increase the linearity of our system. We just use this amplitude response and phase response to impose some phase shifter or some amplitude suppression to our, well, our RF component. So we can make them destructively interference and cancel some unwanted signal in our system.